think about your morning routine for a second. You wake up, you stumble into the bathroom, and you look in the mirror.
Right.
Maybe you run a brush through your hair, you swipe on some deodorant, you might, clip a jagged fingernail.
Yeah, the usual maintenance.
Exactly. Every single day, you are actively managing your hair, your nails, and your sweat glands. We spend, absolutely billions of dollars globally cutting, painting, perfuming, and masking these things.
Oh, easily billions.
And yet, if we're being honest, most of us have no idea how they actually work.
It's so true. We treat them like cosmetic accessories, Like they're just these optional parts bolted onto the outside of the body for decoration.
Right, like aftermarket parts on a car.
Exactly. But biologically speaking, they are highly specialized, highly active systems. In anatomy and physiology, hair, nails, and glands are collectively known as the accessory structures, or the appendages of the integument.
Which just means the skin, right?
Yep, the skin.
So today, we are pulling from a massive stack of sources. We've got classic medical textbooks, historical anatomical journals, and the latest dermatological research to demystify these systems.
It's a really fascinating mix of literature.
It is. And our mission in this deep dive is to understand the hidden mechanics of everyday biology. Because as I realized diving into this research, these structures aren't just bolted on at all. They are born from the skin itself.
Spot on. They are derivatives of the epidermis, which is the outermost layer of your skin.
Okay.
They are specialized modifications that evolve to perform vital jobs that, well, a simple flat sheet of skin just cannot do on its own.
Like what?
We're talking about insulation and sensation with your hair, protection and fine mechanical manipulation with your nails, and complex chemical and thermal regulation through your glands.
Okay, let's unpack this, because before we can really look at what these structures do, we need to understand how they are built in the first place.
Right, the foundations.
Yeah. So I was reading about fetal development, and it seems like a flat sheet of skin doesn't just, spontaneously sprout a hair. It actually digs down first.
That is the perfect way to visualize it. If we look at hair, for example, which starts forming around week 9 to 12 in the womb,
Okay.
the process is called invagination. So instead of building a tower up into the sky, a column of epidermal cells folds downward.
It pushes deep into the underlying layer of tissue, which is called the dermis, right?
Precisely. All three of these appendages, so hair, nails, and glands, they all start this exact same way.
But why dig down? Why not just build on the surface?
Well, because the epidermis itself doesn't have a direct blood supply. It's a remarkably tough barrier, but it's basically a vascular desert.
Oh, wow. So there's no blood up there at all?
None. So by digging that foundation down into the dermis, these structures can tap into a rich network of blood vessels. They rely entirely on the dermis to feed them and, to provide the structural anchoring they need to survive.
Which is a level of complexity that completely eluded doctors for centuries.
Oh, absolutely.
Prior to the 1600s, the medical world was largely operating on the galenic view, right? Just treating the skin like a boring, simple, fleshy wrapper for the organs.
A completely undifferentiated barrier, yeah. That was the prevailing view from the ancient Greek physician Galen all the way until a pioneering scientist named Marcello Malpighi came along.
Malpighi, right?
Yeah, Malpighi was using very rudimentary microscopes. And in 1665, he published a treatise translating to On the External Organ of Touch.
And by putting skin under those early lenses, he totally shattered the galenic view.
He did. He actually illuminated the distinct layers, the papillae, the pores. He proved the skin was a deeply complex, structured organ.
And his name is still literally on the blueprint today. Like in the research, the stratum basal, which is that deep layer of the epidermis that's constantly dividing to make all these structures, it's still sometimes called the Malpighian layer.
A very well-deserved honor, honestly. And the key material those Malpighian cells are churning out to build your hair and nails is a tough structural protein called keratin.
Right, keratin.
It was chemically characterized in the 19th century, and the name actually comes from the Greek word keras, which means horn.
Which is wild to think about. Human hair and fingernails are evolutionarily made of the exact same material as a rhinoceros horn or a bird's beak.
Yeah, nature loves to reuse a good blueprint.
We're basically walking around with modified rhino horns on the tips of our fingers.
We absolutely are. Keratin is incredibly versatile. And if we follow that initial epidermal column down into the dermis, we can see exactly how the body puts that keratin to work. Let's look at the hair follicle.
Yeah, the research describes the follicle as a tube within a tube, right?
Exactly.
And sitting at the very base of this deep dermal foundation is something called the dermal papilla.
Precisely. The dermal papilla is a tiny knot of connective tissue and blood vessels that just pokes up into the base of the follicle. Its sole job is to nourish the hair matrix.
The matrix being where the action happens.
Right, the matrix is a region of rapidly dividing epithelial cells. And as these cells divide, they have nowhere to go but up, so they constantly push the older cells upward.
But as they get pushed up, they're moving away from that blood supply at the papilla. They're basically being pushed out into the desert, like you said.
And that migration is fatal to the cell. As they get pushed upward, they are compressed, they severely dehydrate, they get tightly packed with keratin, and then they die.
Wait. So the hair I brush every morning, the hair we spend all this time washing and styling, is entirely dead.
100% dead.
It's just like a 3D printer buried in my skin, pushing out a lifeless strand of plastic.
It is entirely dead tissue. The visible hair shaft has no living cells whatsoever. It's essentially a three-dimensional fossil of your matrix's activity.
That is slightly terrifying.
A little bit, yeah.
Right.
And that fossil is constructed in 3 concentric layers. The innermost layer is the medulla, though that's sometimes missing in very fine hair. The bulk of the shaft is the cortex, which contains your melanin pigment, so that's what gives your hair its color. And the outermost layer is the cuticle.
The cuticle, that always comes up in shampoo commercials.
That's the one. The cuticle is made of a single layer of overlapping shingle-like cells. When you use certain hair products, you're trying to make those shingles lie flat.
Which makes the hair look shiny and resist tangling.
Exactly. If the cuticles are roughed up, your hair looks dull.
Now, attached to this whole follicle assembly is a tiny muscle called the erector pili. And reading about it, it feels like a total evolutionary leftover.
It is a fascinating piece of anatomy. It's a tiny strip of smooth muscle attached to the side of every single follicle. When you get cold or, when you experience intense fear, your sympathetic nervous system triggers that little muscle to contract.
And it pulls the hair shaft perfectly upright.
Bingo.
Goosebumps.
Exactly. Goosebumps. Now, in our furry mammalian ancestors, this was an incredibly useful thermoregulatory reflex.
Because it traps heat.
Right. If you pull a dense coat of fur upright, you trap a thick layer of air against the skin, which acts as tremendous insulation against the cold. Or, if you're threatened, puffing up your fur makes you look much larger to a predator.
But for modern humans, because we've lost most of our dense body hair, it's practically useless.
Pretty much.
We get a sudden chill, our microscopic muscles pull up our tiny hairs, and we trap absolutely zero air. We just get bumpy skin.
It's a physiological ghost of our evolutionary past. But what's really dynamic about hair isn't just the structure, it's the timing. Hair growth is not continuous. It is highly cyclical.
And this cycle was defined back in 1926 by a British researcher named Frank Dry, right?
Yes, Frank Dry.
Because before him, the scientific language was super vague. People just said hair was growing or resting.
Right, not very scientific.
But Dry observed mice and coined a precise Greek-rooted vocabulary that dermatologists still use today: anagen, catagen, and telogen.
He brought real rigor to the field. So anagen is the active growth phase. For a hair on your scalp, this lasts a remarkably long time, anywhere from 2 to 7 years.
Wow, that's a long time for a cell factory to just keep running.
It is. The matrix is constantly dividing, pushing that dead keratin shaft higher and higher. Then comes catagen, which is a very brief transitional phase lasting 2 to 3 weeks.
What happens then?
The follicle actually shrinks and physically detaches from its blood supply.
Oh, wow,
Yeah.
wow.
Finally, you have telogen, the resting phase. The follicle sits dormant for about 3 months before the old dead hair is shed and a brand new anagen phase begins.
And what's crucial here, and honestly a massive relief, is that every single follicle on your head runs its own independent clock. You're totally asynchronous.
We are very lucky for that. If they were synchronized, we would molt all our hair at once, like a snake shedding its skin.
That would be a terrifying few months.
Right. But because they're independent, roughly 85 to 90% of the follicles on your scalp are in the anagen growth phase at any given moment. Only 10 to 15% are resting in telogen.
Which means if you're panicking because you see 50 to 100 hairs in your shower drain, that is completely normal turnover. It is not pathological hair loss. The factory is just resetting.
What's fascinating here is that hair isn't a fixed, permanent structure. It's actually a state of being for the follicle.
What do you mean?
Well, you have vellus hair, which is that fine, unpigmented peach fuzz on your body. And you have terminal hair, the thick pigmented hair on your scalp or eyebrows.
Right.
During puberty, a follicle producing tiny vellus hair can convert and start producing coarse terminal hair. Conversely, in male pattern baldness, a robust terminal follicle can miniaturize and revert back to producing barely visible vellus hair.
The flexibility of that little cellular factory is incredible, which actually brings up one of the wildest accidents in medical history, the discovery of minoxidil.
Oh, the Rogaine story.
Yes. Back in the 1970s, the pharmaceutical company Upjohn developed an oral drug called Linatin to treat severe high blood pressure. But the doctors noticed a very specific, undeniable side effect.
Hypertrichosis.
Yeah.
Excessive hair growth. The drug was causing patients to grow hair in unexpected ways. Upjohn realized they had stumbled onto something massive, so they reformulated the blood pressure medication into a topical solution. In 1988, the FDA approved it under the name Rogaine.
And the craziest part to me is that even today, the exact mechanism of why it works is still debated.
It's true.
Like, we know it dilates follicular blood vessels and somehow artificially prolongs that anagen growth phase, but the percent cellular mechanism remains a mystery. We capitalize on the side effect without a perfect map of the cause.
Science is often about observing the result before fully mapping the mechanism. And speaking of observing results, the cyclical nature of the matrix perfectly explains why the oldest shaving myth in the book is false.
Oh, the idea that shaving makes your hair grow back thicker and darker?
Yes.
I saw that this was debunked in a controlled study all the way back in 1928.
And repeatedly since then.
But wait, if it's false, why does it feel so true? When I shave, the stubble that grows back feels like a wire brush.
Because it's an optical and tactile illusion. Remember, the anatomy, the living matrix that dictates the thickness, color, and growth rate of the hair is buried deep in the dermis.
Right.
When you shave, you are taking a razor to the dead keratin shaft completely above the skin surface. You aren't touching the factory.
Oh, so the factory has no idea I even shaved.
Exactly. Normally, a hair tapers to a fine, soft point as it grows. When you shave, you slice the shaft at a blunt, harsh angle. When that blunt, wide edge breaches the skin, it feels coarser to the touch.
And because you're seeing the thickest cross-section of a hair against the skin, it visually looks darker.
Yep, but the follicle itself hasn't changed its output at all.
That makes perfect mechanical sense. But here's where it gets really interesting. If hair is an asynchronous on and off factory for keratin, what about our nails? Because they don't seem to have a shedding phase.
They don't. For a long time, medical science treated nails just like inert armor plates. But research from the 1980s onward forced a major reclassification. The nail unit is now recognized as a dynamic, living, four-part organ.
Right, starting beneath the skin. I always assumed the hard plate that we clip and paint was the entire nail, but the research shows the actual factory is hidden.
That hidden factory is the nail matrix tucked away under the skin at the base of your finger. You can actually see the very front edge of it. It's that pale crescent moon shape called the lunula.
Oh, I've always wondered what that was.
Yeah. So the second part is the nail bed, the highly vascular tissue sitting underneath the nail, giving it a healthy pink color. Third is the nail plate itself, the hard keratin shield. And fourth is the eponychium.
The cuticle.
Exactly, the cuticle, acting as a waterproof sealant to block infections from getting into the matrix.
And unlike hair, this matrix is a continuous conveyor belt. On your hands, fingernails grow at a steady rate of about 3 millimeters per month.
Give or take, yeah.
But the research noted toenails grow 3 to 4 times slower. Why the huge discrepancy if they are the exact same organ?
It comes down to blood flow and mechanical stimulation. Your fingertips are constantly tapping, touching, and gripping.
So they get a workout.
Right. They receive incredibly rich blood flow, keeping the matrix highly active. Toes, shoved inside shoes all day, simply don't get the same level of vascular nourishment or physical stimulation.
I found a detail in the research that perfectly illustrates what happens when you just let that conveyor belt run. Have you ever heard of Sridhar Chalal?
The Guinness World Record holder from India.
Yes. He decided to stop cutting the nails on his left hand in 1952.
Wow.
He didn't cut them until 2018. That is 66 years of continuous keratin production.
It's hard to even picture.
When they finally measured them, the combined length of the 5 nails on that single hand was over 29 feet 10 inches.
That is wild.
It's this staggering real-world proof of compound interest, biologically speaking. 3 millimeters a month, never stopping, adding up to nearly 30 feet of solid keratin.
It's an extreme example, but it beautifully highlights the sheer metabolic power of the nail matrix. And because that growth is continuous, doctors view nails as real-time chronological windows into your systemic health.
Like a medical record.
Exactly. Any disruption in your body's supply chain is going to show up in the product.
Like nail clubbing, where the nails become curved and bulbous. The literature flags that as a major clinical indicator of chronic low blood oxygen, often pointing to serious heart or lung disease.
Or Bowes lines, which are deep horizontal ridges running across the nail plate.
What causes those?
They occur when the body is under such severe stress, maybe a massive infection, a high fever, or severe nutritional deficiency, that the nail matrix actually pauses production for a few days to conserve energy for survival.
Oh, wow. So it literally stops the assembly line.
Yes. And once the illness passes, growth resumes, leaving a depressed line in the nail plate. By measuring how far out the line has grown, a doctor can roughly calculate exactly when you were sick months after the fact.
They're like the rings of a tree. That is amazing. Now, before we move on, we have to touch on the creepiest myth in the research. The idea that hair and nails continue to grow after you die.
A very persistent myth, even slipping into early medical texts. But it is categorically false.
Good to know.
Building keratin requires active cell division, which requires blood flow and oxygen. The moment your heart stops, metabolism stops, and keratin production completely ceases.
But why do they look longer in the coffin? I mean, people swear they see it.
Post-mortem skin dehydration. As the body rests, the soft tissues shrink and pull away from the base of the hair shafts and the nail plates. The hard keratin structures don't shrink, so more of them is exposed. They appear to have grown, but it's purely a macabre optical illusion. The factory has been shut down since the time of death.
Okay, so we've covered the keratin factories. If hair is a start-stop factory and nails are a continuous conveyor belt, what happens when that invaginated epidermal blueprint calls for a fluid factory instead?
Glands.
Let's talk about our glands.
For a long time, the taxonomy of our skin glands was quite confused. People assumed all sweat was just sweat. It wasn't until around 1917, and then expanded in 1922, that a German anatomist named Paul Schieferdecker formalized the classification we use today.
And he didn't just map where they were on the body, he categorized them by their mechanism of secretion, which I thought was brilliant. Let's look at the ones connected to our hair follicles, the sebaceous glands.
Right. Sebaceous glands produce sebum, a lipid-rich oil that lubricates the skin and hair. What's fascinating is their mechanism. They use holocrine secretion.
Which is pretty dramatic, right?
It is essentially cellular self-destruction. The gland cell fills up with sebum, and then to release the product, the entire cell ruptures and dies.
Whoa.
The exploded cell is the secretion. The gland then has to rapidly divide basal cells to replace the ones that just blew themselves up.
Kamikaze cellular biology, just to keep my scalp from getting dry. And there's been a massive shift in how we view sebaceous glands and acne, hasn't there? For decades, dermatologists firmly told patients that diet had absolutely nothing to do with acne.
A complete reversal in medical consensus.
We're all like,
Yeah. Recent rigorous studies have proven that the older generation of doctors was wrong. We now know that high glycemic foods and heavy dairy intake spike insulin and insulin-like growth factor pathways in the body.
and that affects the glands.
Directly. Those hormonal pathways directly stimulate the sebaceous glands to overproduce sebum, leading to acne. The old wives' tale about diet mattering was actually right.
Science revising itself based on better data. I love it. From the oil glands, let's move to the true sweat glands, the eccrine glands.
Unlike the explosive sebaceous glands, eccrine glands use merocrine secretion.
Which means?
They produce a watery fluid and gently release it via exocytosis, packaging the fluid in tiny vesicles and pushing it out without damaging the cell at all. You have roughly 2 to 4 million of these scattered across your body.
And their primary job is evaporative cooling. Most mammals cannot dissipate heat like we can. An endurance athlete running a marathon in the heat can lose over a liter of sweat per hour from their eccrine glands.
And up to 14 liters in a day in extreme conditions.
Which is insane. This is why sports drinks push electrolytes so hard, right? You are literally pouring sodium out of your body to keep the engine from overheating.
It is vital physiological science. But we also need to debunk a major myth here. The idea that sweating detoxifies the body. You see this in sauna marketing all the time.
Oh yeah, sweat out the toxins.
Biologically, it's nonsense. Your liver and your kidneys are your detoxification organs. The singular purpose of eccrine sweat is cooling. The tiny amounts of metabolic waste in sweat are just trace byproducts.
So it's not actually cleaning you out.
No, sweating to detox is like turning on your car's air conditioner and expecting it to change the oil.
That is a great analogy. Wait, hold on. If eccrine glands are making me sweat buckets during a run, and apocrine glands are the ones in my armpits, why doesn't my running sweat smell bad? Aren't they both just sweat?
This is a great distinction. Apocrine glands are localized to the armpit and anogenital regions, and they only become active during puberty. They don't produce that watery cooling fluid. They produce a thicker protein and lipid-rich secretion. But when that apocrine sweat leaves the gland, it is completely odorless.
Wait, really? So where does the body odor come from?
The bacteria on your skin, they eat the proteins and lipids in that apocrine sweat and excrete waste, and that byproduct is what causes body odor.
Ew.
Right. Your running sweat from the eccrine glands is mostly water and salt, which the bacteria don't feed on in the same way.
Which exposes some incredibly sloppy science in the multi-billion-dollar hygiene industry.
How so?
Think about antiperspirants versus deodorants. Antiperspirants use aluminum salts to physically plug up the eccrine ducts to stop moisture.
Right.
Deodorants, on the other hand, don't stop the sweat. They use antimicrobials to kill the bacteria feeding on the apocrine sweat. Two entirely different targets, constantly mashed together in commercials as just fighting sweat.
It's sloppy taxonomy for a lucrative market, and that taxonomy actually expanded in the 1980s, by the way. A researcher named Sato discovered a third variant, the apocrine gland. It's a hybrid in the armpit that develops during puberty. It secretes the thin, watery fluid of an eccrine gland, but at a massively higher continuous rate. It completely broke the old two-box system.
Biology is never as simple as the textbooks want it to be. To wrap this up, the research highlighted one incredible example of how these eccrine glands act as a diagnostic window, specifically regarding cystic fibrosis.
Yes. If we connect this to the bigger picture, the cystic fibrosis sweat test is a marvel. Cystic fibrosis is a devastating genetic disease affecting the lungs and pancreas. In the 1950s, a researcher named Paul de Santagnese realized patients with CF had a defect in a specific cellular chloride channel.
The CFTR channel, right?
Exactly.
And because eccrine sweat glands normally use that exact same channel to reabsorb sodium chloride from sweat before it leaves the body, a broken channel means the chloride gets left behind and the sweat comes out abnormally salty.
You hit the nail on the head. To this day, the frontline diagnostic tool for a fatal internal organ disease is to simply measure the chloride concentration in the sweat of a skin gland.
That is incredible. So, what does this all mean for you? We've journeyed from fetal cells digging deep into your dermis, to the asynchronous 3D printers making your hair, to the unstoppable keratin conveyor belts of your nails, and the millions of microscopic fluid factories regulating your temperature.
It's a lot going on right under the surface.
It really is. These accessory structures are not just cosmetic afterthoughts. They are highly evolved systems that tell a story about our ancestral past and broadcast real-time alerts about our internal health.
They are the body's dynamic interface with the outside world.
Absolutely. And I want to leave you with a thought to mull over. If a doctor in the 1950s could diagnose a complex genetic lung disease just by measuring the salt on your skin, imagine the future of wearable technology.
Well, that's a great point.
As medical sensors get incredibly small, we are looking at a near future where your smartwatch doesn't just track your pulse. Imagine a wearable patch that continuously samples the trace metabolites in your eccrine sweat or monitors the real-time cellular shifts in your hair follicles.
It would be revolutionary.
Your skin's accessory structures could soon act as a 24/7 non-invasive molecular dashboard, broadcasting your entire internal biological state to the outside world. So the next time you're standing in front of the mirror, brushing your hair or swiping on deodorant, just remember, you aren't just looking at dead keratin and annoying sweat. You're looking at an absolute marvel of biology. Thanks for joining us on this deep dive. Keep questioning the amazing systems hiding in plain sight.